This we talked about yesterday. By the conclusion of today's conversation, in conjunction with what I think we can accomplish successfully tomorrow, I'll decide where material content for Exam 1 terminates. And I will let you know by posting a note about this on our homepage, as well as asking the graduate student instructors for the discussion classes to tell you about this tomorrow during discussion class. Note that Part 1, which is page 1, each exam will consist of 3 pages. We'll be here concurrent with the lecture time for Friday, except that this Friday we'll have you engaged in a great deal of fun. Page 1 of Exam 1. I will ask that you arrive by 1:50 p.m. so we can get you started, give you plenty of time. I really try to make as much time available as I can for you folks. The idea being, I want to find out what you know. And I don't know that I can achieve that successfully if I squeeze you for time. So it's always my intention to provide far more time than is required to work through the exam if you know what's going on. Keeping in mind that if you don't know what's going on, I can give you a month. Wouldn't do any good. And also remember, you get the information sheet. If you've downloaded such from the home page, you know exactly what the information sheet will contain. So you don't have to memorize information like acids and bases and Ka values and stuff like that. Part 2 will also be Friday, starting at 7 p.m. I have a feeling you'll be able to find the location without any great difficulty. So, for each of these events on Friday, we will ask, please, that you sit well apart from each other. I think that we'll have no difficulty doing that because we don't have a whole lot of you and we've got almost 300 seats in here. So we proceed with more considerations in regard to buffer systems, or systems which may have been prepared, which behave like buffers, but not necessarily for the purpose of functioning as buffers. For example, question 1840. We are imagining to be issued 100 milliliter sample of 10th molar acetic acid to 2 sig figs. So we start by recognizing that we have an acetic acid solution which contains 0.010 moles of acetic acid. We're going to treat this with some sodium hydroxide solution, which is 10th molar, in order to generate a pH of 5.00. The reason why this behaves like a buffer system is that the reaction which will occur on treatment with hydroxide ion is to convert acetic acid molecules to acetate ion. But since we're not killing all the acetic acid, we're going to wind up with a solution that's got both acetic acid and its conjugate base acetate ion present in high concentration. So just like a buffer. Question is, what volume of sodium hydroxide must be added to achieve this? I trust by now you have recognized that first and foremost important aspect of dealing with any problems like this, any problems which involve reactions. Here's the reaction that occurs in this system when we add the hydroxide ion. What's most important? I asked you this yesterday. I'll ask again. What is most important? You always have to keep a handle on what the system contains. Without knowing what's in the system, you cannot possibly deal with its chemistry. Of course, on knowing what's in the system, then you have every opportunity to deal with the chemistry of the system. Inventory. And for problems like this, the inventory must be quantitative in addition to qualitative. And when we talk quantitative inventory in chemistry, what are we talking about? For each component, how many moles? That's right. So back to our sodium hydroxide treated acetic acid solution. We start with 1/100th of a mole to 2 significant figures of acetic acid molecule. We add hydroxide ion, represented by X. But we're not going to add sufficient hydroxide ion to equal or exceed moles of acetic acid. So after this treatment, there'll be a considerable molarity of acetic acid remaining. But this treatment will also establish a considerable molarity of acetate ion. Here's the equilibrium constant expression for our acetic acid solution, rearranged so that we see how the acetate ion concentration relative to the acetic acid concentration depends on pH, depends on the hydronium ion concentration. So on generating a pH of 5.00, which corresponds to hydronium ion concentration of 1.0 times 10 to the minus 5, what we are recognizing is that we are trying to construct an acetic acid acetate ion buffer which has this concentration ratio for these ingredients. So this shows us the ratio of conjugate base to Bronsted-Lowry acid. Or we could just as well write base to conjugate acid, controls pH, or vice versa. By fixing pH for any solution of a weak acid or weak base, you fix the ratio of the ionizing acid solute relative to its conjugate base. You fix the ratio of molarities of these species. We're going to be examining that consideration many times as we proceed. So, given that we looked at this yesterday, here's the reaction. X represents moles of hydroxide ion added, which also represents moles of acetate ion made. And this ratio tells us, at this pH of 5.00, moles of acetate ion is equal to 1.8 times moles of acetic acid. And notice I can say moles rather than concentration. Why so? Why can I read this as a ratio of moles and not necessarily read it as a ratio of concentrations? These species, acetic acid and acetate ion, are in the same solution, aren't they? Well, if I wanted this to be concentration, I take moles and divide it by volume up top, and in the denominator I take moles and divide it by the same volume. So this division by volume is not necessary for this case. So I can read this as a ratio of moles. So I write this, I do the arithmetic. This is the mole amount of hydroxide ion that I have to add because I'm making this many moles of acetate ion by clobbering acetic acid. I'll get this concentration ratio. I'll get my pH of 5.00. I'll get this hydronium ion concentration. So at a glance, I hope you can recognize that if with this solution I want to supply to this system 0.0064 moles of hydroxide ion, I got to add 64 milliliters. End of problem. Now, Question 1841. This is a takeoff on a question which you have already tackled. Specifically, you tackled it in your last discussion class gathering. The system to which I refer is a mixture of hydrochloric acid solution with sodium sulfide solution. In this case, we're asked to consider mixing 300 milliliters of 0.050 molar HCl with 100 milliliters of the sodium sulfide solution, 10th molar, as opposed to question 1822, where we combine 200 milliliters of this solution with 100 milliliters of this solution. So relative to question 1822, in making this mixture, we are supplying more moles of hydronium ion. And we want to see what impact that has on the resulting system inventory, or specifically hydronium ion concentration and pH. Chemistry. Our inventory tells us in the mix we make, hydronium ion is the strongest acid, hydroxide ion is the strongest base. This reaction goes, and of course it goes to a very large extent. This is really the KW reaction in reverse. This reaction kills 0.010 moles of hydronium ion, which will then leave behind 0.0050 moles of hydronium ion, and kills all the initial hydroxide ion. So we have to, at this point, re-examine the inventory. And re-examining the inventory at this point, we have a system where all initial moles of hydroxide ion have been wiped out. We still have 0.010 moles of HS minus to consider. We don't care about the 0.015 moles of chloride ion because chloride ion has no impact on pH. And the quantity of hydronium ion has now been reduced to 0.0050 moles. So I'm still obligated to pay attention to my inventory in order to answer the question, is there any other chemistry which occurs in this system? The answer is you betcha. Hydronium ion is the best acid still remaining in inventory. Now the strongest base remaining in the inventory, the best base is hydrogen sulfide ion. Do hydronium ion and hydrogen sulfide ion react with each other to a large extent and produce H2S and water respectively? You know how to play this game. You look at the acid-base table, you recognize that hydronium ion is a considerably stronger acid than H2S, and hydrogen sulfide ion is a considerably stronger base than water, so you know this is also a large extent reaction. Consequently, this reaction effectively produces H2S. What happens from a stoichiometry standpoint? We now wiped out the remaining 0.0050 moles of initial hydronium ion and wiped out half the initial moles of hydrogen sulfide ion. 0.010 less the 0.0050, resulting in making 0.0050 moles of H2S. So what do we now have? An H2S HS minus buffer. One for which the hydronium ion calculation is quite simple. Because in this particular H2S HS minus buffer, the HS minus and H2S molarities are equal. This treatment reduced this to 0.0050 moles remaining, and this treatment at the same time produced 0.0050 moles of this. That's why these molarities cancel, giving us a hydronium ion concentration that's the same as Ka for H2S. Now you can do the pH arithmetic, get 6.96. Ever so slightly smaller than 7.00, given that this value is ever so slightly larger than 1.0 times 10 to minus 7. So this solution is very mildly acidic. But as we reminded ourselves, what gave us the opportunity to be successful with this calculation? Keeping a handle on inventory throughout. Question 1842. We're going to consider making two mixtures. First mixture, 5.0 milliliters of deionized water treated with 5 drops of 0.50 molar hydrogen chloride solution, hydrochloric acid. To do this, we need to have a handle on the volume of 1 drop aqueous liquid. That's about 0.050 milliliters. Anybody remember getting this value? Does this value look familiar to you? Did you do 45 laboratory here? Did you do assignment 1? We had you do some really challenging things like count drops. Like that. Because if, for example, while you're at work in 46 laboratory, you're doing an experiment on a small scale basis and it requires, say for example, a half a milliliter of a particular solution. Do you want to take the time required to get out your 10 milliliter graduated cylinder and rinse it with that solution and throw stuff away and then collect the half milliliter and then pour the half milliliter from the graduated cylinder and recognize that a lot of the liquid stays in the cylinder because the cylinder is hydrophilic? It's rather electric in nature because of the materials from which we make glass. And so the solution stays in there, so you got to put DI water in there and rinse it and transfer the rinsings. And you got to put more in there and transfer the rinsings if you want to be sure to get all the solution. I'd much rather get some of the parent solution in a small, clean beaker, vial, take a clean dropper, draw up some of the solution, and count. Boing, 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 boing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 drops. And now I got my half a milliliter. Don't you think that's easier? Well, you keep that in mind when you're at work at 46L. I think you'll find that's a whole lot easier and a whole lot quicker. That's why this is handy information. In any case, determining the hydronium ion concentration for the solution, that results when I put together the deionized water with the HCl solution. That's simple stoichiometry for a solution, simple stoichiometry analysis. No chemistry's going on. All you're really doing in combining the deionized water with this solution is diluting the hydronium ion. That's all you're really doing. So you figure out how many total moles of hydronium ion you got in this HCl solution, because the amount of hydronium ion in the HCl solution is enormous relative to the tiny amount of hydronium ion in the DI water. You get 1.25 times 10 to minus 4 total moles of hydronium ion. We got 5 drops of this solution, so that's 0.25 milliliters. So we'll add that to our 5.0 milliliters. That gives us the total system volume of 5.25 times 10 to minus 3 liters. And we get a solution which has got a hydronium ion concentration of 0.024 molar. Now comes the fun part. We will, for the second part of this experiment, consider mixing 5.0 milliliters of half molar acetic acid solution with our 5 drops of our 0.50 molar HCl. You have any recollection of what the pH is for half molar acetic acid solution? Got any recollection of that from what we've already done in class, from what you've done in laboratory? In assignment 1 laboratory, you were asked to approximate the pH for 1 molar acetic acid. Anybody remember what you got? 2.4. That is the pH, the one significant figure for 1 molar acetic acid. 10th molar acetic acid is pH 2.9. You probably got a value of about 3.0 because you're using the eyeballs, which are pretty good devices, generally better for the gals than for the guys. It's just a genetic fact that females see colors better than males. May make you better chemists. So, and we did a demonstration on this when we were looking at indicators and the like. Remember when I took the 1 molar acetic acid, about a couple hundred milliliters, and put it together with a couple hundred milliliters of deionized water, and I said, predict the colors? Trying to remind you before we made the mix that for that mixture, with the acetic acid solution showing a distinct red with methyl orange indicator, and the deionized water showing what I call goldenrod, a pretty color. Now when you mix those two systems, all you were really doing was diluting 1 molar acetic acid to half molar, not changing the hydronium ion concentration much at all. The hydronium ion concentration for half molar acetic acid is about 2.6. So no color change was observed. We preserved the distinct red color of the acetic acid solution. Question is, if I have a pH on the order of 2.6 for my half molar acetic acid solution, 2.6, which corresponds to a hydronium ion concentration of about, how much? 2.6 pH. What kind of a hydronium ion concentration does that correspond to? About. Any idea? pH 2.6. Doesn't that tell you the hydronium ion concentration is smaller than 1 times 10 to the minus 2, but greater than 1 times 10 to the minus 3? Can we start with that? Okay, we're in there someplace. One of the questions the laboratory asked you, in order to have you recognize that concentrations relate to each other exponentially, unlike pHs, which relate to each other linearly, because pHs are logs. That when you use an indicator and you have an indicator-treated solution which contains a known pH, like the hydrochloric acid solutions you use as standard, and you now look at a solution whose hydronium ion concentration is not known, treated with the same indicator, and you get a solution which is comparable in color to the standard solution, the one for which you know the pH. In trying to determine the hydronium ion concentration for the unknown solution, the solution whose hydronium ion concentration you don't know, do you think it's easier to try to approximate for the unknown solution its hydronium ion concentration directly or its pH directly? What's easier? What did you do in lab? Yeah, it went at pH. Because the pHs correlate linearly. If you see a color which you believe is halfway between two distinct shades, like yellow, green, and you see a yellow-green color, and your eyeball is saying, that thing looks to me like it's equal in character yellow and green. It's halfway between color-wise yellow and green. And the yellow is pH 2.0. And the green is pH 3.0. We've already played this game. You ascribe to the yellow-green solution, which looks to be 50% green, 50% yellow, a pH of 2.5. Now, for the yellow solution, the hydronium ion concentration at a pH of 2.0 is 1 times 10 to the minus 2. For the green solution, hydronium ion concentration 1 times 10 to the minus 3. One of the questions that we asked you in laboratory for assignment 1 is, what's the hydronium ion concentration that's halfway between 1 times 10 to the minus 2 and 1 times 10 to the minus 3? What's the hydronium ion concentration that's halfway between those boundary values? What is it? How are you going to get it? Are you going to take the boundary value concentrations and add them up and divide by 2? You can do that, but you won't get the right answer. To have you recognize that concentrations are exponential in nature, the halfway hydronium ion concentration these values is the hydronium ion concentration that differs from the boundary values by the same factor. That's the halfway hydronium ion concentration. And getting that is oftentimes not particularly simple from an arithmetic standpoint. But if you do this with pHs, it's very simple. You take the pH for this, the pH for this, add them up, divide by 2. Just like when we approximated Ka values for indicators and the like. That's easy. pH 2.0, pH 3.0, calculator 5.0. Calculator again, divide by 2. 2.5. And now I need the hydronium ion concentration corresponding to a pH of 2.5. How do I get that? Well, I get that by recognizing that, by definition, the log of 1 is 0. The log of 2 to 4 significant figures is 0.3010. The log of 3 to 4 significant figures is 0.4771. The log of 4 is twice the log of 2, so I don't have to remember that one. The log of 5 to 4 significant figures is 0.6990. The log of 6 is the log of 2 added to the log of 3. So I don't have to remember that one either. The log of 7 to 4 significant figures is 0.8451. The log of 8, I don't have to remember that either, because it's 3 times the log of 2, because 2 cubed is 8. Log of 9, I don't have to remember that either, because that's the log of 3 doubled, because 3 squared is 9. And the log of 10 to 4 significant figures is 1.0000, where all the zeros in this case are significant. And with this, I can do gee whiz pH arithmetic all over the place. And I don't need calculators, except the best one we all have, this one. I mean, what I just cited to you, to some of you, may sound like magic. Not magic. When I sat in your seat long ago, I took general chemistry at the University of Toledo in the fall of 1960. You think we had calculators? Well, we had to do this arithmetic. So I said, heck, let me remember these log values, and they've stuck with me. And with the log values I just cited, you can do gee whiz pH calculations all the time. And usually, if you need a pH determined only to one significant figure, hey, you don't need a pocket calculator. Just use the data I just reported to you. So if I have a pH of 2.5, okay, given that the log of 3 to 4 significant figures is 0.4771, which is 0.5 to 1 significant figure, I know that the hydronium ion concentration that's halfway between these two values is 3 times 10 to minus 3. But I'll bet you, after what we just did, you will say, by golly, it sure as hell is a lot easier to approximate pHs with indicator analysis and then compute the hydronium ion concentration. Don't try to approximate the hydronium ion concentration straight away. Okay. All of that to get back to our acetic acid solution treated with the HCl solution. This has a pH of about 2.6. It's got a hydronium ion concentration that's a little bit smaller than this. Question. When we make the acetic acid, hydrochloric acid solution mixture, will I get a hydronium ion concentration? Which is larger than this number. That's the $64 question. Do you recognize that in making this mixture, the hydronium ion concentration has got to be at least this? Because in making this mixture, I established this concentration by putting the hydrochloric acid solution 5 drops in this 5 ml volume of this acid solution. So I'm guaranteeing the hydronium ion concentration is at least this. Will this reaction, right here, the ionization equilibrium established by acetic acid reacting with water, will this reaction in this system, will this reaction still contribute to the resulting system hydronium ion concentration? Will hydronium ion concentration for this mixture be equal to or be greater than 0.024 molar? Well, let's have a vote. How many vote that the added hydronium ion, the hydronium ion supplied to the system by adding the 5 drops of the HCl solution, is going to shove this reaction so far right to left that this thing is no longer going to be capable of contributing measurably to the resulting solution hydronium ion concentration? If that statement is true, for this solution, the hydronium ion concentration is this. But if this goes to an appreciable extent, then the hydronium ion concentration for this system will be greater than this. 2 possibilities exist. How many vote that the added hydronium ion is going to suppress the ability of the ionization of acetic acid to the extent that this acetic acid treated HCl solution will have a hydronium ion concentration of 0.024 molar? How many vote that? How many vote that this solution is going to have a hydronium ion concentration that's a lot bigger than 0.024 molar? How many vote that the acetic acid solution will have a hydronium ion concentration that's bigger than 0.024 molar, but not very much bigger? I'm getting a lot of half of votes. Maybe it's heavy air. Can't lift up the air today. Well, let's find out. Here's the chemical version of the acid ionization constant for acetic acid, which we've looked at already many, many times. So, the stoichiometry of this system is now X for the acetate ion concentration. Label on the bottle 0.50 minus what? Minus X. And the hydronium ion concentration is what? Don't tell me X. It's 0.024 plus X. Because I got two sources of hydronium ion now. The contribution from the added HCl solution and the contribution from the ionization reaction of acetic acid with water. So we've done the chemistry. Now let's do the arithmetic. Whoops. There's the expression we have to deal with. What we're trying to find out, whoops, pardon me. What we're trying to find out is X big enough? X is the contribution made to the overall hydronium ion concentration by the ionization of acetic acid. Is X big enough such that when I add it to 0.024, I get a number bigger than 0.024? That's what I'm trying to find out. Now, to pursue this further, you've got to understand significant figures. So I'm going to write this down. What value for X? What is the smallest possible value for X such that when I add X to this, this gets bigger? What's the smallest possible value for X such that when I add X to this, this will get bigger? Well, if this is going to get bigger by only the smallest possible amount, what's the answer? 0.025. That's right. So X to the third decimal place has got to be 1 in the third decimal place. So is it possible that X could be, because notice all the data we have is the two significant figures. I'll write this over here. Could X be 0.0060? And change this to this. Would this do it? Because when I do this, I'm forced to round to the third decimal place. If I round this to the third decimal place, what do I get? 0.001, don't I? Could x be 0.00051? If I round this to the third decimal place, do I get a 1 over here? Mm-hmm. So, what I'm going to do is to find out if x is as large as 0.00051. Because if x is that large, the hydronium ion concentration for our acetic acid solution is going to be bigger than this number. Now, to do that, I'm going to write in here, in my mind's eye, I'm going to write x equals 0.00050. So, here's x. If I take 0.00050 and subtract it from this, do I change this? Nope. So I can forget this. So I've got 0.024 plus this number times this number divided by this number. That's what I have to do to answer this question. Is this arithmetic difficult? Because I got 0.50 in the denominator and 5.0 times 10 to minus 4 in the numerator, don't I? See that? 0.50 in the denominator and 5.0 times 10 to minus 4 in the numerator. If I divide this, what do I get? 5.0 times 10 to minus 4. Divided by 0.50. What's this give me? What does it give me? What's the result of this? Exponent? Minus 3. So this tells me if x is this value, this term becomes 2.4 times 10 to the minus 5. How does 2.4 times 10 to the minus 5 compare to this? 2.4 times 10 to the minus 5 is bigger than this, isn't it? What does that tell me about the true value for x? Is the true value for x bigger or smaller than this number? Smaller. So guess what? This solution has a hydronium ion concentration of that. We just proved it. Now, back to question 1843. Pardon me. Back to question 1835, from which we will do 1843. You remember 1835 involving our imaginary indicator, gator xanthus, and the acid solution of HQ, or the solution of acid HQ. What we need to know from question 1835 to wrestle with question 1843. Well, you tell me what we need to know. What do we need to know from question 1835? Here's what's at issue. We are imagining to take the HQ solution, which we analyzed for question 1835. The one which had a pH of 1.3. The one with Gator xanthus that showed a distinct yellow-green color. A color that we took halfway between yellow and green. Straight yellow was shown by Gator xanthus at a pH of 0.9 or lower. And straight green was shown at a pH of 1.7. So this yellow-green, which we imagine to be 50% yellow character, 50% green in character, had a pH of 1.3. We're going to take this HQ solution with a pH of 1.3, and we're going to treat it with sodium hydroxide solution. In order to change the yellow-green color to green color, we're going to change the pH from 1.3, that was the pH of our HQ solution from question 1835. We're going to change the pH from 1.3 to pH of 1.7. How much sodium hydroxide is required to achieve this? That's the question. Now, in addition to the information which we have just discussed, what else do we need to know from question 1835? I ask this because I have discovered that when folks don't know how to deal with these questions and problems, it's a consequence of not knowing what the heck the question or problem requires. But you now know what these questions and problems all require, don't you? What is it? What is it? I-N-V-E-N-T-O-R-Y. Inventory. If you don't know what's in the system, you can't deal with its chemistry. So what inventory consideration do we still need to know from question 1835? We know pH, we know observed color, we know Ka for HQ, because question 1835 told us that KAHQ was the same as Ka for the indicator, and that we found to be 2 times 10 to the minus 2. What else do we need to know? What else do we need to know? If you're not going to tell me, then I don't see why I should tell you. Because maybe I don't know. But maybe for $1 from everybody, then I'll know. Be surprised how I can be subject to playing dirty politics. What else do we need to know? What inventory consideration do we need to know?
How much there is.
How much there is of what?
The solutions.
How much there is of the solution? All right, go back to 1835. You got your notes. What do we have, 1835? Are we looking at 1835? Well, what are we seeing? How much HQ solution? 1 liter? I'm taking your word for it. I'm not looking at it. And for 1835, we wound up computing m sub I for the HQ solution, didn't we? What did we get? What'd we get? That what we got? Okay. Now, when I go about treating the HQ solution from question 1835 with sodium hydroxide, will a reaction occur? Am I not going to result in changing the pH? You think a reaction is going to occur? On your paper right now, I want you to write the equation for the reaction that occurs. Do it. How many wrote this? Good. Because in our HQ solution, the principal acid is HQ. And we added hydroxide ion. What's the extent of this? Large or small? I'll put quotes on that, because I want you to tell me why you know this is large extent. Large is correct, but tell me why. I didn't hear you.
HQ is a stronger acid than H2O, and HO is a stronger base than Q.
How do you know this?
Didn't it have like a pH of 1.3 by itself?
How do you know that HQ is a good deal stronger acid than water, but a weaker acid than hydronium ion? How do you know this?
Calculated the K.
Look at this number. You got Ka values in the acid-base table? Mm-hmm. But this is a lot smaller than Ka for hydronium ion, isn't it? But it's a lot bigger than Ka for water. So I know this is a large extent reaction. In other words, I know this reaction effectively converts HQ to Q minus. Okay? Now, back to this. I'm trying to make a pH of 1.7. What's hydronium ion concentration at a pH of 1.7? Well, I'm going to go back to this log table that I told you about just a moment ago. And tell you, number one, is this correct? Number two, will I accept this? Never. Because if you want to play with fractional exponents, I'm going to send you to the laboratory and tell you to make me this solution. And you're going to say, what the hell am I going to do with this fractional exponent? That's dirty, isn't it? I don't want to see any fractional exponents written on concentrations on the exam, because I'm taking my red pen out and go, don't do that. Now you can say, what the hell is that? Well, I'm going to show you what I did. Long ago, when I had log tables that contained logs only of numbers which were larger than 1. Now, logs of numbers that are smaller than 1 have what kind of sign? Negative. Okay? And a pH is a negative log, isn't it? This is minus 1.7. That's why I wrote the hydronium ion concentration equals 1 times 10 to the minus 1.7, which is arithmetically perfectly correct. But from a communication standpoint and from a simplification of chemistry standpoint, that's no way to express a concentration. So I'm going to play a game with this negative log. Minus 1.7. That's what this is. I'm going to take and add to this minus 1. Only to the characteristic. That gives me minus 2. But if all I do to this number is add minus 1, I change it. I don't want to change it. So when I add minus 1, I'm going to also add plus 1. But I'm going to add the plus 1 to the mantissa. What's plus 1 added to minus 0.7? What's plus 1 added to minus 0.7? Plus 0.3. You see, if I add minus 2 to plus 0.3, I get minus 1.7, don't I? So I took that number and I wrote it like this. I'm telling you, this is the same as this, except here the whole thing is negative. Here only this part is negative. This part is positive. That's why I wrote the positive hat up here. Because I'm going to go back to my log table. Because in my mind I know that the log of 2 to 4 significant figures is 0.3010. Which tells me that the hydronium ion concentration for this solution is the antilog of 0.3 times 10 to the minus 2, and the antilog of 0.3 is 2. Now, I don't expect you to do these pH calculations like I do them. But I am hoping that I have shown you, you can do them. You're going to have to sit down and in a very torturous, painful fashion, memorize those log values just like I did. How long do you think that'll take you? Maybe 5 minutes? And then you got them with you forever. If you use them often, like I do. So here's what we got. Now, watch out. Because in the HQ solution that we are treating, you see this label on the bottle. Okay? But in the HQ solution we are treating, what is in fact the HQ molarity? We found this out when we solved question 1835. It's the inventory business again. M sub I was the label on the bottle. M sub I was the label on the bottle. M sub I is 0.2. But the true HQ molarity in that solution was not 0.2, was it? because a good deal of the HQ converted to Q minus in 1835. I'll write this down on the board. See if that looks familiar. There's the molarity of Q minus. That is present in the HQ solution for 1835. So if that's the label on the bottle for HQ, how much HQ is actually in that solution? Question 1835. How'd you get that? You believe this? This is the X for the HQ solution. There's the label on the bottle. This is how much Q minus I actually had. So how much of the HQ had to disappear to give me this Q minus concentration? This much. Right? So the actual HQ molarity in here, we'll write down HQ actual equals 0.2 minus 0.05 equals 0.15. Now I know I'm cheating on significant figures, but we'll fix the significant figure problem at the end of the calculation. So we have this. And in the denominator, we have this. And now I can solve this thing for Q minus, because I only have one unknown. What do we get for Q minus? Well, 0.1 really. So, if we find that the Q minus molarity winds up being 0.1, and we know this is the chemistry that occurs when we treated the HQ solution with hydroxide ion, and we know that in the HQ solution we treated, we had a Q minus molarity of 0.05. We got 0.15 minus X. Here's X. And this is 0.05 plus X. Well, if Q minus winds up being 0.1, what's X? If Q minus winds up being 0.1, what's X? What do I have to add to 0.5 to turn it into 0.1? 0.05. So, How much sodium hydroxide did I have to add? 0.05 moles. Hold on. But, how did we succeed in getting this? By paying attention to inventory throughout. That's the only way. Now, let me take the remaining few minutes to show you what you're going to continue with tomorrow. You want to be there because I know that this stuff, the stuff that I'm now going to make mention of, introduce you to, will be part of exam 1. Two solutions. The first one says hydronium ion concentration for 3 times 10 to the minus 8 molar HCl. Second one says hydronium ion concentration for 5 times 10 to the minus 8 molar sodium hydroxide. Before we do any arithmetic, I want you to give me an approximate pH value for each solution before we do any arithmetic. This solution. Anybody? 6.9. Anybody have a different suggestion? Anybody with still a different suggestion? All right. Now I want to ask a question about this solution. Is this solution guaranteed to be acidic? Did I not make this solution by dissolving hydrogen chloride in water? And hydrogen chloride is a strong Bronsted acid, an acid which ionizes to an extent of 100%. That guarantees this solution is acidic. That guarantees it cannot have a pH above what value? 7.0. This can't be right. Now let's look at this solution. Do you see that this solution is, in one respect like this solution, it's also very, very dilute? But this solution was prepared by dissolving a source of hydroxide ion in water. So I know for a fact, before I do any arithmetic on this solution, it's got to have a pH that compares how to 7.0? Equal to or greater. So I'll write it this way. And for this, I'll change this to this. Because what we're introducing you to now is the recognition. When you are of a mind to determine hydronium ion concentration or pH for a very, very dilute solution of an acid or a very, very dilute solution of a base, beside the contribution that's made to the solution's pH by the solute acid or the solute base, what else do you have to consider? Yes. Must always consider Kw, which is the numerical representation for the ionization of water, in calc of pH for the dilute solution of a BLA or BLB. So you're going to look at that tomorrow. And I expect also some stuff on ionization extent. If you want to take a look at the notes, my expectations are that for exam 1, we'll hold you responsible for all the stuff through page 1840. I'm stopping a little short of where I usually stop, but I don't care. I want you to digest this stuff successfully. Okay?
So the exercise that's on Friday, we just bring it into the part 1. The exercise that's on Friday, we bring it into part 1.
What exercise?
The recovering board.
I didn't have an exercise on
Is
there.
that exercise 1 to Friday?
No, X was exam.
Oh, all right.
Exam 1 is entirely going to be Friday.
All right. Exam 1 is entirely on Friday?
Yep.
Okay.
That's what we decided yesterday.
Okay. I have a question about your particular here. When I did it, I got 0.3. Because to divide both
Did it?
by this equation right here.
You got what?
I divided both sides by 2 to the negative 2, multiplied both sides by 0.15 minus q not, or minus q minus, and then added q minus to both sides, got 2q minus equals.
Well, maybe I wrote the wrong thing down. Oh, I should have wrote this. Because I'm wanting M sub I there. That's what I should have wrote, M sub I. I think when I discussed this, I made
So that was
an incorrect statement.
Okay, yeah. All right.
Okay, yeah.
both parts of the exam are only going to cover for page 840 or just the one?
1840.
1840.
Yeah.
Just on both parts?
Yeah.
The,
I'll put a note about this on the webpage.
Good afternoon, Dr. Harbaugh. My name's Todd Sahagan. You told me to come to see you during the third week of summer A.
Okay, and you are, well, can you see me next week?
Yes, sir.
Good. See me at the start of next week. This week I got an exam going on.
Understood.
And see me on Monday and we'll be able to fix you up.
Sure thing.
Okay?
Thank you for your time.
What exactly is the deal for the exam? I think I walked in late yesterday.
The deal?
Yeah, it's all on Friday, so
Yeah.
it's a shorter exam?
No.
Okay.
It's 3 pages, legal.
Okay.
Part 1 is 1 page, for which you get about 90 minutes.
Okay.
Part 2, they give you 3 hours. 2 pages.
So it'll just run after, will it all be in here? Or?
Yeah, I had it on the board. You didn't see the note?
No, I didn't.
Okay. Part 1, I want you all to show up about 1:50.
150.
Yeah, and I'll let you work till 3:30 for page 1, part 1.
Okay.
And then part 2 is in the evening, 7 to 10 p.m., right here.
7:10 p.m. right here?
Okay, this isn't kind of related, but you said you're going to put the lessons on YouTube, right? Do you know when you're going to have that done? Because
I got to get the bugs worked out of it first.
it'll be nice to start.
Yeah, it's not there yet.
right.
Yeah, I know. I want them on there as soon as possible.
Yeah, because it'd be really nice to start.
Yeah, I understand. I want it there too.
Do you have an answer key for your notes?
No.
Questions, you don't have like an answer key?
That's right, I don't, on purpose.
So what about the questions where you don't have like an explanation or answer given?
Then you have to see us.
Okay.
And we'll be glad to discuss them with you.
Okay. So I just see one of the TAs.
Or me.
Or you?
Yeah, sure.
Okay. Sounds good. Thanks.
I know what's wrong. Screen isn't low enough. That easily visible?
There's no way to tell for sure how it's going to look on the screen.
Well, that's why we want to find out. I'll run the screen lower to capture the whole thing.
Is this the reduced version that you had Xeroxed? Remember you said you had Xeroxed the reduced version?
Yeah, should be a reduced version.
Just making sure.
Maybe I'll need to reduce it even more. Bungle that. That barely gets it in. I'm going to have to reduce this some more.
Well, I've got the whole thing. Now I just have to convert it and see how it looks on the computer.
Yeah, well, that's all we want to do is see how it looks. We'll take it from there. All right.